In this video, we're going to go over some examples of computing improper integrals. But before I get to that, I want to discuss a few definitions and some notes on limits. Okay, so first the definitions. So if you compute an improper integral and it's a finite number, we say that the integral converges. And then if it goes to an infinite number, then the integral diverges. Okay, so those are the two definitions, and I also want to discuss computing some limits. So let's review some common limits. So if n is any number bigger than 0, then the limit as x goes to infinity of 1 over x to the n, this is always equal to 0. So that's the first one. If again n is greater than 0, you take the limit as x goes to infinity of x to the n. So here the numbers are getting bigger and bigger, so this goes to infinity. The limit as x goes to infinity of e to the x, this goes to infinity. The limit as x goes to minus infinity of e to the x, so e to the minus infinity, this goes to 0. So you should think of it as e to the minus infinity goes to 0. The limit as x goes to 0 from the right, the natural log of x, equals minus infinity. The limit as x goes to minus infinity of the inverse tangent of x, this goes to minus pi over 4, and the limit as x goes to infinity of the inverse tangent of x, this goes to pi over 4. So these are some common limits that you should be familiar with. Okay, so let's compute some improper integrals. So the first example will be to integrate from minus infinity to 0 of 1 over 1 plus x squared dx. Okay, so the infinite limit is on the left-hand point. So we set up the proper limit. So this can be the limit as a goes to minus infinity of the integral from a to 0 of 1 over 1 plus x squared dx. Okay, so now we evaluate the integral first, and then we take the limit. Okay, so the antiderivative of 1 over 1 plus x squared is the inverse tangent. Evaluate from a to 0. So now plugging in the endpoints. So at 0 you get inverse tangent of 0. And then if you plug in a, you get the inverse tangent of a. Inverse tangent of 0 is 0. So it's 0 minus this limit. But as we see above, as x goes to minus infinity, the inverse tangent goes to minus pi over 4. So this is 0 minus a negative pi over 4. And so the total is equal to pi over 4. So this improper integral converges. Okay, so let's take a look at another example of an improper integral. So in this example, we're going to integrate from 0 to infinity of x e to the minus x dx. Okay, so the function is x times e to the minus x, so we need to use integration by parts. So let's remember the formula. So the formula for integration by parts is the integral of u dv is equal to u v minus the integral of v du. So in this case, we're going to take u to be x and dv to be e to the minus x dx. So du, so the derivative of x is 1, so du is 1 times dx. And then we integrate dv, so the integral of e to the minus x is minus e to the minus x. Okay, so now let's write it out. So u times v would be minus x e to the minus x. So I'm going to cheat a little bit and write this part as 0 to infinity. So I'll introduce the limits later. And then minus the integral of v du, the integral from 0 to infinity of minus, so v is minus e to the minus x. And then du is equal to dx. So the two minus signs cancel and they become plus. So this is minus x e to the minus x evaluated from 0 to infinity. So I'll explain this later. So then the two minus signs cancel out and becomes a plus. Okay, so then we have to find the antiderivative of e to the minus x. The antiderivative of e to the minus x is minus e to the minus x. This is minus e to the minus x. So again, that we're taking the antiderivative of this to compute this improper integral, and then this is going from 0 to infinity. Okay, so again, I'm cheating a little bit, but we'll introduce the limits later. Okay, so then at infinity, we have to compute that as a limit. So this is the limit as x goes to infinity of minus x e to the minus x and then at the other endpoint, if you plug in 0, x is 0, so that 0 times anything is 0, so that's minus 0. And then in this part, again, at infinity, we have to compute that as a limit. So that's the limit as x goes to infinity of minus e to the minus x. Then minus, when we plug in 0, e to the 0 is equal to 1. But then there's a minus on here, so that's minus 1. So that's the second part here. So again, to keep track of everything, this part here is coming from this, and this part here is coming from this part. Right, so I'm evaluating at the two endpoints. Whenever I see an infinity, I introduce a limit, and whenever it's just a number, I plug it in as I normally would. Okay, so then we have this expression. So now I just need to compute these two limits. Okay, so let me rewrite this as a fraction, right? So the negative exponent I can bring down. So that's the limit as x goes to infinity of minus x over e to the x, and that's just 0. Okay, so as x goes to infinity, so this is e to the minus infinity, which we know from above, e to the minus infinity goes to 0. So this whole thing goes to 0, and then minus 1 becomes plus 1. So now all that's left is to compute this limit. So as x goes to infinity, so there's a few ways to do it. You can use L'Hopital's rule, and then you get minus 1 over e to the x, and then e to the x goes to infinity, so you get 1 over infinity, which goes to 0. Or you can think about it as growth of functions, right? So in terms of growth of functions, the exponential function grows much faster than x, and so that means that this limit must go to 0. So this also goes to 0, and so this is equal to 1. Okay, so again, this integral converges to 1.